This lecture is on Artin-Rees lemma in commutative algebra. So let's see what is Artin-Rees lemma. Artin-Rees lemma. This lemma is about the special properties of Noetherian ring. Further, this lemma is used to prove the cruel intersection theorem, which we will see in the further videos. But as of now, we are going to see the proof of Artin-Rees lemma. So let me state the lemma. This lemma says that let R be a Noetherian ring. We have a Noetherian ring R. Let's suppose A is any ideal of R, an ideal of R, and M be any finitely generated module. R module, which is a module over R. M is a R module. And let's suppose that M prime be a submodule of M. Then there exists an integer from natural number such that, well, this notation is for ideal A. AIM intersection M prime is equals to AI minus K AK M intersection M prime. Okay, so we have to prove this interesting property, the power preserving property you can see here. But anyways, for all exponents I is greater than K. So before coming to the proof of this lemma, we need to discuss some topology. We are a special kind of a topology which we are going to induce on R. So let's talk about a little bit about the A-adic topology. So observe that the descending sequence of ideals, since R is Noetherian, A and so on, defines a topology, and the very special name is assigned to this topology is known as A-adic topology, where A is an ideal. A-adic topology. Anyways, so now we are, if this is a topology, then let's talk about open sets. So how open sets are defined for this special kind of topology, A-adic topology. So a subset E of R is called open if for every element, every single element of X, every single element of this subset of R, there exists an exponent or index I of that ideal A, such that X plus ideal to the index I is contained in R, is contained in E. Okay, this is known as open sets. This is defined as an open set of this A-adic topology. Okay, so this open set E is defined in such a way. Now, thus the powers of an ideal for I in N are basic open neighborhoods Okay, if we put x is equals to 0 here, x is equals to 0, then the powers of AI will act as a open neighborhoods of 0, because this forms an open set of E. So if we are required to find out the neighborhood of 0, then the powers of ideal A, the index of ideal A are nothing but the basic open neighborhoods. So of the zero element in R, zero element in that ring. Now, uh, just like we defined a array topology on this ring, similarly we can induce this same topology on the module, that R module. So let's define let's see how this topology works for this R module M. So the A-adic topology, the A-adic topology, the A-adic topology on any R module M by taking the submodules AI of M, AIM, submodule AIM, where I is from natural number, as a basic open sets, basic open neighborhood of the element 0 in M. Now if we have some module M prime of N, then we can restrict this A-adic topology. So let's see how to restrict this A-adic topology. So if we have M prime, which is a submodule of M, and we want to restrict this A-adic topology, then we can just restrict this by taking the intersection AIM, AIM, which we have used for the topology on the module M intersection M prime. Now this A-adic topology is now restricted to M, since M prime is contained in this. Now a subset. Now if we have restricted this topology, then again we want to see that how open sets will look like. So thus a subset E, which is inside, earlier we took a subset from a ring, now we are taking a subset from a submodule, okay, is open if and only if for x from E there exists an exponent I from natural number, such that in a similar way we are going to write for this. So x plus AIM intersection M prime is contained inside E. Okay, we saw how this topology, the A-adic topology, has been restricted to the sum module M prime. Now if but on the other hand, you can see that naturally this this M prime sum module has induced topology, a induced A-adic topology as a submodule of M. So we need to compare that induced topology, because by default it has a topology. If this has a A-adic topology, induced A-adic topology, then this by default as a submodule it will also have a A-adic topology, but here we have a restrictions, and so we need to compare the both topology. That means first topology is this, and the other topology we are going to see, then we have to compare both topologies. So let's on we observe that on M prime the A-adic topology exists as well, and we may try to compare both topologies, which I have explained earlier. Okay, we have to compare both topologies. So observe that AI M is contained inside AI M intersection M prime, because it's a subset of this, and M prime is a submodule of M. So obviously any subset E of M prime that is open with respect to the restriction of A-adic topology, on M restriction of on M will be on this A-adic topology. We have restricted the topology on M to M prime. Now will be open with respect to the A-adic topology on M prime. So here you need to look that if it is a subset of M prime, and it is open with respect to the restriction of A-adic topology on that module M. So by naturally it will be open with respect to A-adic topology on M prime, because it is a sum M prime is a submodule of M. So now to prove the Artin-Rees lemma, we have to show that the open set which we have obtained by the restriction of A-adic topology on the submodule M prime is equals to this term, and this automatically this is contained inside this. Let me tell you that we are nothing but doing the reverse inclusion. First we saw that AI M prime is contained inside AI M intersection M prime. Now now we have to show that this term is contained inside this one, this term is included in this one, and here on the place of AI M prime I have written AI minus K M prime to make it in a more general sense. This is a part of the Artin-Rees lemma. So before going forward, let me tell you a very interesting thing. This A-adic topology is a Hausdorff topology. Now why this is a Hausdorff topology? So we all know that the topology is called Hausdorff topology if it satisfies the Hausdorff separation axiom. So let me write the Hausdorff separation axiom. So a topology on a set X is said to satisfy the Hausdorff separation axiom if any different points x comma y from X admits disjoint open neighborhoods. Okay, open neighborhoods. Now we have on the place of X we have our ring R, which is Noetherian ring. So two cosets, since a ring is a group, so two coset with respect to the ideal AI exponent with exponent AI, ideal AI are either disjoint or same. So, so let me write this. Since two cosets with respect to AI, AI is an ideal with exponent I in R with respect to AI are disjoint. So if they are disjoint in case of a ring, then we can say that they are disjoint in case of a module also. That means with respect to AIM in M, they will be disjoint, as soon as they do not coincide. So we need to we can say that the intersection of AIM is equals to 0. So AIM is equals to 0. This means that this topology satisfies the Hausdorff axiom, because two cosets either they are disjoint or they are identical. So in our case they are disjoint with respect to AIM. With respect to AI, first they are with respect to AI, and then in the case of module also they are disjoint. So it satisfies the Hausdorff separation axiom. So the A-adic topology is Hausdorff topology. Okay, now we can go further and see little more things before doing actual proof of the Artin-Rees lemma. So we have a Noetherian ring R. Our ring is Noetherian ring. Noetherian ring R, and we have a ideal. We have considered an ideal A, of R, and an R module M, which is of a finite type, together with an A filtration. The A filtration, which is represented as, now by filtration I mean that there exists a descending chain of ideals, homogeny. In the case of some modules, we have a descending chain of some modules. That means M is equals to M naught contains M1 and so on, such that AI Mj is contained inside Mi plus j for all I comma j belongs to natural number. So this is a definition of filtration. Filtration means the module M of a finite type, then we are going to induce a filtration, which means that we have a descending chain such that this axiom holds, that says that a exponent of an ideal A Mg is contained inside Mi plus j for all indexes from natural number. So now this filtration is astable. This filtration, if there exist if there exists an index, if there is k such that mi plus 1 is equals to ideal mi. So this, the filtration which we had made, this filtration, this is called alpha A stable if this following property holds. Now more generally we can say that equivalently if mk plus I is equals to ai mk, again I have included k to make it more general, to make it look like a more general, because we need, in the proof of Artin-Rees lemma, we need a more general sense of this statement. So for all I j I belongs to, for all I from natural number and I is greater than equal to k. Okay, now we need to introduce the notion of graded ring. So let me show you a little bit about graded rings. So here, this is algebraic geometry with Robin have shown. So here you can study the definition of graded rings. A graded ring is a ring S together with a decomposition such that direct or decomposition of S into a direct sum of abelian group SD, such that for any indexes d comma e greater than 0, SD dot SE is contained inside SD plus E. So this is what I am going to use here. So so furthermore, let us consider the direct sum R dot. Now we are going to say that this ring as a graded ring, which is defined as the direct sum I from n ai as a ring by using component wise addition and by distributively extending the canonical multiplication maps ai cross aj ai plus j. That is a condition of to form a graded ring for I comma j. So this is nothing but the whole definition of a graded ring. So we are going to construct this a graded ring. So we need these two things, and now in a similar way we can just like we have constructed a graded ring, we can construct a graded module. So we can view the direct sum m dot, which we are going to say that a graded module as an R dot module. Okay, this is an R dot module, just like this is an R module, R submodule. This is submodule of M. M is a R module. Now this is a graded ring, this is a graded module. Observation: R dot is a Noetherian. Now this fact I am not going to prove. because it will take more time, but it is not a very difficult task. You have to make some adjustment and use Hilbert basis theorem. Hilbert basis theorem, and it is very easy to show that R dot is Noetherian too. Now I'm heading forward and write a lemma which is important in order to prove the Artin-Rees lemma. And again, I'm not going to cover the proof of that lemma in this video, because otherwise this video will become so lengthy. So lemma. So for a Noetherian ring R, an ideal A of R and an R module of finite type let graded ring R and M dot graded module as before, then the following conditions are equivalent. Then the following conditions are equivalent. So the conditions are the filtration Mi is A stable, ideal stable, and second, the graded module is an R dot module of finite type. Proof. The proof I will cover in the further video. I will not cover in this video. I will be focusing more towards the proof of Artin-Rees lemma. The things like Krull intersection theorem and this lemma will be covered in the further videos. Now, if we have established all the necessary tools which are useful for which will be used to prove the Artin-Rees lemma. So now consider the filtration Mi I from n of M by Mi is equals to Ai. So we have considered a filtration like this. Now this filtration is astable. This filtration, I'm telling you why. This filtration is astable. Why? Because remember what I have said for the stable filtration. So when I wrote the general condition, so just put k is equals to 0 here. When you put k is equals to 0 here, the m0 will be nothing but the R module M itself. So Mi is equals to Ai and k. Very easy. So it's a stable by its definition only. Now furthermore, we are going to consider an induced filtration. So consider the induced filtration M dash I from n on M prime. So we are now going to consider induced filtration on a some module of M. So we have represented this like this here. So where Mi prime is given by Mi intersection M prime. Okay, so now observe that the graded module M prime is canonically an R dot submodule of M dot, because since M dot is of finite type, since M dot is of finite type. M dot is of finite type, and the lemma which I have wrote earlier, the lemma is this: for a Noetherian ring R, an ideal A of R and an R module M of finite type. M dot is of finite type, and let R dot and M dot as before. The filtration Mi is A stable, and M dot is an R dot module of finite type. So we have a condition that M dot is an R dot module of finite type. So since M dot is of finite type, we can say that from that lemma, and since R dot is Noetherian, uh, uh, M dot star is of finite type as well, because there is a result which says that for a ring R, the following conditions are equal. Let me write that result. This is a very elementary result in the commutative ring theory. For a ring R, the following conditions are equivalent. Conditions are equivalent. What are those conditions? Number one, R is Noetherian. Number two, every R module M of finite type is Noetherian. Okay, so here we have M dot is a R dot module which is of finite type. So M dot is Noetherian itself. That means that some module M dot will become a finite type by this property. Now, so by the lemma which we have covered before, by that lemma, the filtration Mi prime I from n is A stable, where is an ideal. A stable and there exists an integer k such that A of Mi prime is equals to Mi plus 1 prime for I is greater than equal to k. So from here A of Mi prime is nothing but, so observe that let me write the values. So Mi prime was nothing but A of AIM, and Mi prime is Mi intersection M prime. So we will use these values to get our desired results. So A of Mi prime is nothing but, use the value Mi intersection A of Mi intersection M bar M prime, and which is equals to Mi is equals to AIM. So A of AIM intersection M prime. And if we look at RHS, so Mi plus 1 prime is equals to Mi plus 1 intersection M prime, and Mi plus 1 is nothing but Mi plus 1, put the value I plus 1 wherever here is I, so Mi plus 1 will nothing but AI plus 1 M and intersection M. So from LHS we got this, and from RHS we got this. That was the Artin-Rees lemma. So A, which is an ideal, let me bold it because it represents an ideal. A of AIM intersection M prime is equals to AI plus 1 M intersection AIM intersection. Okay, so this is Artin-Rees lemma, and if we iterate the process, we would get for a general K that A of I A K M intersection M prime is equals to A K plus I M intersection M prime. That was the result we wanted to prove. So this was all about Artin-Rees lemma. Further we will cover Krull intersection theorem and the proof of that lemma, which I have covered but not proved, which I have used to prove this Artin-Rees lemma. So thank you very much.